The first trend I like to look at is atomic radius, and if you look at the periodic table, this is a cross section of your periodic table. As we go across a period, for example period 3, if you follow the elements, you see sodium is 160 picometers, then magnesium gets smaller, 140, aluminum gets smaller. So the trend is as you go across, atomic radius gets smaller. So let's just write that. So atomic radii decreases as we go across. Now the reasoning, you have to be able to justify it. It's simply because you have more protons and you have the same number of shells. So number of shells are not changing. But as we go across a nuclear charge, or simply number of protons increase while number of shells. Now remember, number of shells is same as your period number. Stays the same. So this is one fundamental property. Students usually get it wrong, so please try to remember as you go across, atomic radii get smaller. It gets smaller in size. Now what happens as you go down a group? That is a little simpler to look at. So when you go down, for example, if you look at lithium compared to sodium, sodium gets bigger. Compared to potassium, potassium gets bigger. Now why is that? Because you're adding more shells of electrons, and therefore they are further away from nucleus. So period 4 has 4 shells compared to period 3. So as you go down, atomic radii increases. And the reason for that is either shielding increases or simply you have more shells. So as we go down, a group, atomic radii simply increases. Why is that? You should just remember, because now you're simply having more shells. Since we have more shells of electrons. And since number of inner electrons or inner shells go up, this is also saying the shielding is increasing. So shielding increases. The layers, inner electron layers, are protecting their valence electrons. Now looking at the other properties of periodic table, physically what I want you to recall is 2 very important properties. One is first ionization energy. In your data booklet, it's on the upper left corner. For example, then again, let's just keep track of period 3 as we go across. 496 for sodium, while for magnesium is 738. So ionization energy increases as you go across. Why is that? Because now you're closer to the nucleus and you have difficult time to lose your valence electrons. There is more energy involved. So as we go across, ionization energy increases. The other property I want you to pay attention to is electronegativity, the ability of the atom to attract the shared electrons. As you go across, the same thing happens. Just like ionization energy, it increases. And you should remember fluorine is the most electronegative. Then after that, the other 2 tiny elements of oxygen and nitrogen. The closer you are to fluorine, the more electronegative you are. Now if you keep track of going down a group, if you look at ionization energy of sodium versus potassium, you see in this case it's decreasing. So as you go down, you have easier time to lose your valence electron, because it's further away from the nucleus. And also the same trend goes as you go down a group, electronegativity decreases. And then if you remember cesium as the least electronegative, and if you remember fluorine as the most electronegative, then you have easy time to argue many of the chemical properties. So fluorine the most electronegative. In the case of cesium, it's also known as the most electropositive. It's a metal likes to lose its electron rather than gain electron. So you can also remember it as the most electropositive. And in chemistry, then again, we have a diagonal rule. This is a resultant of a vector. As you go up, electronegativity increases. As you go across, electronegativity increases. Now let's look at one other property, melting point, which melting point depends on the structure and also the attractions among the atoms. The first three elements going, then again, we are following period 3. So if you look at the first three elements, they are metals. Sodium is metal, magnesium is metal, aluminum is metal. And what do they have is metallic bonding. Now metallic bonding is, metallic bond is proportional to a ratio known as charge density. Number of valence electrons divided by or over the atomic radius. The smaller atomic radius and the more valence electron you have, the stronger the metallic bond. In case of magnesium, it's 2+. In case of sodium, it's 1+. Magnesium is smaller in size, therefore it has higher melting point. So sometimes you are given a graph like this and you should recognize it as melting point graph. This is, for example, sodium, about 97 degrees Celsius to melt it. This is magnesium. Aluminum and magnesium are close, but aluminum is slightly higher. Now let's see what happens to silicon. Silicon and carbon, you should remember, those are giant covalent. They're not simple, and the melting point is high. So silicon has a structure of giant covalent or macromolecule, and you have to break all the bonds, and that's why silicon is the highest. It's up here. Now what happens to phosphorus and sulfur and chlorine? They simply become simple covalent. They're not giant covalent. So these three groups categorically are simple covalent, and what they have to offer is just London dispersion or van der Waals. This is phosphorus. In nature, phosphorus comes in group of 4, and it's a simple covalent. And sulfur, you will find it as a plastic, yellow plastic, which 8 of them travel together, S8. Then chlorine is diatomic gas. And finally, you have argon, which is monatomic gas in that series. If you keep track of at least group 1, as you go down group 1, you should realize that the melting point sort of decreases. So cesium is almost liquid-like at room temperature. It's very close to that. Why is it lower in melting point? Because the metallic bond, as you go down, decreases. You have 1+ for all of them, but cesium is the bulkiest, the biggest. Therefore, this ratio sort of gets smaller, and metallic bond is weaker. So as you go group 1, alkali metals, the melting point decreases. Now there is an opposite relationship. When you go to group 17, halogens, the reverse happens. Fluorine is a diatomic yellow gas. So at room temperature, it's a gas, and you see it has negative value for melting point. Chlorine is a green gas, diatomic. They're all carcinogenics. These two are gases. Bromine is also a red liquid. So bromine is becoming liquid. And finally, iodine is a purple solid.